In this tutorial, we'll look at some common questions in the topic of rate of reaction. There are three important parts to this chapter, the first of which is on the experiments that we can conduct in the lab in order to determine the rate of a reaction. The second important part is the use of collision theory or ideas about colliding particles to explain how the 5 factors that affect rate actually take place, actually influence the rate of the reaction. And the very last part is to be able to analyze graphs or to be able to predict how the graphs will look like if any of the 5 conditions were to be changed. So first we'll look at questions involving experimental design. In the O-level syllabus, if you are ever asked to describe an experiment that you can conduct to measure the rate of a reaction, 90% of the time it will be for a reaction that produces a gas. Because when a reaction produces a gas, we can easily follow the progress using 2 methods. The first method is to measure the volume of gas produced over time. So in this case, the rate will be simply given by the volume of gas produced per unit time. So the setup for such an experiment will be similar to that of setup 2, where you need an apparatus for collecting and measuring the volume of gas, and that will be the gas syringe, and then we will need to pair it with a stopwatch. The second method in which we can follow the progress of the reaction for reactions producing a gas is to measure the change in mass or the loss in mass over time. So why would the mass of your reactant mixture change? It's because when a gas is produced, your gas is going to be released, is going to escape from your reaction mixture. As a result, the total mass of your reaction mixture will decrease with time, and we can then calculate the rate by taking the change in mass per unit time. And to do that, we need an experimental setup similar to that in setup 1, where we have our reaction mixture being placed on an electronic balance, which will give us the mass of your total reaction mixture at different points in time. So one thing to take note is that there's also a cotton wool over here. The cotton wool is to prevent any liquids from coming out of your reaction flask, but at the same time it will allow your gas to pass through and be given out to the atmosphere. So for this question, let us first look at the reaction involved. The reaction is that between a carbonate and an acid. We have learned in the syllabus that when an acid reacts with a carbonate, it will produce a gas in the form of carbon dioxide. So this is ideal. As mentioned, we can then follow the rate of the reaction using either the change in volume of gas produced with time or the loss in mass of your reaction mixture with time. So setups 1 and 2 would be ideal. Now let us take a look at setup 3. For setup 3, the difference or the method that we are building on would be the change in volume or volume of gas produced with time. Over here, instead of using a gas syringe, remember we have learned different ways of gas collection, and one of them is by displacement of water. So this setup 3 makes use of the displacement of water. Now, so would this setup be suitable for measuring the rate of reaction for this particular reaction? It looks okay, even though carbon dioxide is slightly soluble in water. I think it is still an okay setup. However, if you look at the setup closely, there is the use of a thistle funnel as opposed to a tap funnel in setup 2. Now a thistle funnel, as the diagram shows, do not have a tap. So there isn't a tap over here, meaning it is open. It is meaning when a gas produced, the gas can actually escape from this opening as well. So that is the flaw in this experimental design. So even though displacement of water is an acceptable gas collection method for carbon dioxide, but in this setup, the Tissot funnel should be replaced with a tap funnel if we were to use this method. So for this question, the answer is B, 1 and 2 only. For this question, again, we are asked to describe an experiment to follow the progress and to calculate the speed. So once again, let us take a look at the reaction. The reaction is between an acid and a reactive metal, which again produces a gas. So as described earlier very extensively, when you have a reaction that produces a gas, there are two methods for measuring the rate. The first method involves measuring the volume of gas produced with time. The second method involves the monitoring of the change in mass of your reaction mixture over time. The setup for measuring the volume of gas, you need a gas syringe. This is the most basic of setup. And then for measuring the change in mass, you need a flask on an electronic balance with a cotton wool to prevent any liquid from coming out, but at the same time allowing the gas to escape into the air. For the respective setups, we can then find rate as the change in volume of gas over time per unit time, or the change in mass per unit time. Now we'll look at questions where we will make use of collision theory to explain how the different factors can affect the rate of a reaction. Now just a quick recap, what is collision theory? Collision theory states two things. Number one, for any chemical reaction to occur, your reactant particles must first collide. And the second thing about the theory is that the particles must not only collide, they must collide with sufficient energy, with energy greater than or equals to the activation energy before a reaction can occur. When a collision has, when two particles collide with energy greater than or equals to activation energy, then we say that that is an effective collision. So in this case, we are looking at the reaction between zinc and sulfuric acid. So reactive metal plus acid gives you salt and hydrogen gas. The question requires you to use collision theory. So a hint in the question is this: whenever you see using ideas about collisions, means that you have to make use of collision theory. How rate of reaction changes when the concentration of acid is increased. So this is what I would call a routine question. Before you sit for your O-levels, you should have already memorized the explanation for such a question. When your concentration of your acid increases, the number of particles per unit volume increases. Okay, over here the per unit volume is important. When you simply say number of particles increase, it doesn't translate into concentration increases. So you have to say number of particles per unit volume increases. That means that the particles are closer together, and what happens is that then your frequency of collisions would increase. And when your frequency of collision increases, your frequency of effective collisions would then also increase, and therefore your rate would increase. For this question, now we are looking at the effect of temperature. When temperature is decreased, again this is a routine question. When temperature decreases, the kinetic energy of your particles would decrease. Okay, so what effect would that have on your particles? The frequency of collisions would increase. the frequency of collisions would decrease, and another important factor is this: the fraction or the number of particles with energy greater than or equal to activation energy would decrease. Now that the particles have lesser energy, the number of particles with sufficient or enough energy for an effective collision would therefore be lesser. So that is an important factor. Now, due to these two factors, your frequency of effective collisions would then decrease, and therefore rate would decrease. So for this question, it's similar to the one before, but this time we're going to use collision theory to explain how particle size affects rate. So for this question, we are looking at the reaction of an acid with a reactive metal in the form of magnesium. And for this question, we are replacing magnesium powder with a magnesium ribbon. And there are two parts to this question. The first part is to state what happens to the rate, and second part is to explain using collision theory. So once again, we know that's collision theory because they mention collisions between particles. So to state what happens to the rate of reaction, I think this is simple. When we replace powder with ribbon, I think it's very obvious that your particle size increases, so therefore the rate would decrease. And then how do we explain for that using collision theory is this: that when your particle size increase, your total surface area exposed for reaction would actually decrease. And when that happens, the frequency of collisions between your reacting particles would decrease, and that would cause a decrease in the frequency of effective collisions. Now we'll look at the factor of catalysts on the speed of a reaction. So we have learned in the syllabus that a catalyst can speed up a reaction, and the catalyst does it by providing an alternative pathway with a lower activation energy. Now, other than that, there are some other characteristics or features of a catalyst that you must keep in mind. So what are they? They are, number one, catalyst is chemically unchanged in a reaction. Okay, it may be physically changed, the appearance may change, the state may change, but it will be chemically unchanged. So because it's chemically unchanged, we don't need to use a lot of it. So for this question, the particular feature that I just mentioned is actually the answer over here. So the question tells you that the catalyst in the oxidation of sulfur dioxide to sulfur trioxide is nitrogen 4 oxide or nitrogen dioxide. So nitrogen dioxide speeds up the rate of reaction. What other property? Over here you can see that there is a multi-step, there's a two-step reaction. And over in the first step, nitrogen dioxide, which is the catalyst, actually takes part in the reaction. So it is not true, if you have read it somewhere, that a catalyst do not take part in the reaction, therefore it's chemically unchanged. Catalyst can take part in the reaction, but how does it stay chemically unchanged? Is that it will be regenerated in a later step. Okay, so for catalysts, how do they stay chemically unchanged if they are taking part in a reaction? Is that they will be regenerated at the end of the reaction. So the property that we're looking at is that nitrogen dioxide, being a catalyst, is chemically unchanged at the end of the reaction. So over here we are asked to illustrate the effect of catalyst on the rate of reaction using an energy profile diagram. So as stated earlier, a catalyst speeds up the reaction by providing an alternate pathway which involves a lower activation energy. So to draw the energy profile diagram of an uncatalyzed reaction, you would expect to see a greater energy barrier. So this would be for the uncatalyzed reaction. So EA, the original activation energy. And then for the catalyzed reaction, you would expect to see one with a smaller energy barrier. So let's call this EA prime. So EA prime is that of the catalyzed, and EA will be the uncatalyzed. So one thing to take note over here is that the catalyst, it doesn't affect the enthalpy change of the reaction. It only affects the energy barrier for a reaction to occur. Now for the last part of the video, we'll look at questions related to the graphs, to interpreting the graphs that we can obtain from the experiments described earlier. So as mentioned, one way to follow the rate of a reaction is to measure the volume of gas produced with time. So if we were to plot the volume of gas produced with time for a reaction, it will look like something that you will see in this question. So for this question, the reaction produces sulfur dioxide gas. Now when we have a graph of volume of gas with time, there are few things that we can take note of. The first of which is the rate of the reaction is given by the gradient. So if we look at the gradient at the start, or the gradient to the tangent of the curve at the start, it is large, it decreases over time, and eventually it reaches zero. When the gradient reaches zero, it simply means that the rate is zero, meaning the reaction is complete or the reaction has stopped. So over here, for any reaction, due to the reactants being used up, you would expect the rate of reaction to slow down or to become lesser, and therefore the gradient to become gradually less and less steep. So let's analyze the four options here to determine which statement is correct. For statement A, the gas can be collected by displacement of water. Remember, displacement of water is to collect gases that are insoluble in water. In this case, sulfur dioxide is very soluble. In fact, it is the pollutant, if you can recall, it is the pollutant that contributes to acid rain. So it's very soluble in water, so you should not be using displacement of water to collect the gas. Next, the mass of the reaction flask and its contents would decrease as the reaction proceeds. Now, as mentioned earlier, whenever a reaction produces a gas, the gas can escape from the reaction flask. So the mass of the reaction flask and its contents would decrease over time. So B is the correct answer. For C, the rate of reaction increases as time increases. So this is obviously wrong, because the rate of the reaction as shown by the gradient is decreasing. And then last one, the reaction is still proceeding after 8 minutes. So how do we know when the reaction stops? Is to see when the gradient reaches zero, and that appears to be around 5 minutes. So by 8 minutes, it is no longer proceeding. So D is also wrong. For this question, we are again looking at a graph, but very importantly, you need to take note of the axis of the graph. In this case, we are no longer looking at volume of gas with time, but we are looking at rate of reaction with time. Now, as mentioned, as seen earlier in the graph of volume of gas with time, the rate of reaction is the highest at the start. It decreases as the reaction proceeds, and it reaches zero at a certain point in time. So the correct graph that we are looking at for how rate changes with time is that there is a finite and maximum value at the start, it decreases over time to 0. So the correct answer would be D. For this graph, we are looking at the second method where we look at the loss in mass over time. So when we have, now even though we are looking at the different experimental approach, the fact that the rate of reaction would decrease over time remains unchanged. So in this case, how would it be reflected in the graph is this, that the rate is reflected by the gradient. In this case, the negative gradient, because the mass actually decreases. So over here, we would expect the gradient to be the steepest or have the maximum magnitude at the start, becomes gentler in the middle, and then eventually reaching 0 at a point in time. So at this stage, there seem to be two graphs that fit the description. Let me just strike out A and B first. So C and D seem to fit the description. So which one is correct? If you just look at the experiment, would the mass of your content and flask reach 0? The answer is no, because there will, even if all your reaction mixture were to magically disappear, your flask would still measure a certain mass. So the mass of your flask and content would remain constant at a finite value. For this question, it is slightly more complicated because we are looking at now two different graphs for experiment 1 and experiment 2, and we're supposed to translate volume of gas over time into rate of reaction over time. Now this question can be solved more easily if you can recall this, that whenever we look at the rate of reaction graphs, there are three important points that we must focus on. What are the three important points? The three important points are this: the initial gradient, which reflects the initial rate. Second is the final volume of gas. And the last one would be the time at which the reaction is complete. So for any speed of reaction or rate of reaction graphs, it will be good for you to focus on these 3 points. So for this question, the important ones would be 1 and 3. Let us look at the initial gradient for experiments 1 and 2. You can see that the gradient for experiment 1 is actually steeper than that for experiment 2. What does that mean? It means that at the start, the rate of reaction for experiment 1 is larger or higher than that of experiment 2. That means that we can cross out options B and C. Next, in this case, the final volume of gas, even though there is a difference, it doesn't carry much meaning. It doesn't help you much in solving this question. We'll look at point number 3, the time at which reaction is complete. Once again, how do we know the time at which the reaction is complete? Is to find the time at which the gradient reaches 0. So in this case, we can see that experiment 1 actually is complete before experiment 2, meaning the rate would go down to 0 even earlier, at an earlier time as compared to experiment 2. So that means that the correct answer here must be A. So once again, we are given two graphs, a question of two graphs from two different experiments. So the question states that graph number 1 is obtained from an experiment of the decomposition of hydrogen peroxide, and then for you to deduce which of the options would produce graph number 2. Now the approach is the same. We need to look at the 3 points on the graph. The first point is the initial gradient. So as you can see, the initial gradient for graph number 2 is actually less steep than graph number 1. So what it means is that the rate of reaction is actually lower. So whatever change there was to experiment 2, it caused the reaction to slow down. The second important point to look at is the final volume of gas. As you can see in experiment 2, the final volume of gas increased, and that can only happen when the amount of your limiting reactant is increased. In this reaction, there's only one reactant, so that means that the amount of hydrogen peroxide must increase. So if we were to look at the options immediately, you should be able to tell me that B is the correct answer. Okay, but for learning purposes, let's go through the wrong options before we come back to B. Now for A, if you were to lower the temperature of the reaction, it would definitely cause reaction 2 or experiment 2 to have a slower rate. However, changing the temperature would not affect the final volume of gas. So A is wrong. For C, using less of your catalyst. Now catalyst, as mentioned, is chemically unchanged. We only need a small amount of it. So the amount of catalyst used is actually quite insignificant. It doesn't affect the rate of a reaction as long as the catalyst is present. Using a different catalyst in D may affect the rate of the reaction, especially if the catalyst is not an effective one, the rate would decrease. But once again, a catalyst will not affect the yield or the amount of gas that is produced. For B, if you are adding some more hydrogen peroxide solution, definitely we will get more gas produced. But at this point in time, some of y'all may be asking, if we were to add some more hydrogen peroxide, wouldn't the concentration increase? And therefore the initial rate to be higher as well. Now the important thing about this question, unfortunately, which was cut off by my cropping, is that the initial concentration of hydrogen peroxide is 1 mole per dm cube. And if you look at option B, you are adding some 0.1 mole hydrogen peroxide to the original solution. You are adding a less concentrated or a more diluted solution into a concentrated one. Okay, so what will happen to the final concentration? It will be lower, and therefore the initial rate would be lower as well. We will look at one last graphical question. Again, there are 2 experiments, experiment 1 and experiment 2. And we are asked to predict which graph would correspond to the conditions stated. So once again, we will focus on the 3 important points of a graph. Now, the difference between experiment 1 and 2, if you can see, would be the concentration of acid. So experiment 2 has a higher concentration of acid. If we have a higher concentration of acid, we would expect the initial gradient of experiment 2 to be larger than that of experiment 1. So we can cross out B and D. The next point that we look out on the graph is the final volume of gas, which is affected by the amount of your limiting reactant. In this case, your limiting reactant is actually, we don't even have to find out which one is limiting, because if you were to look at the amounts of both reactants, even though the concentration of sulfuric acid was changed in experiment 2, the number of moles remained unchanged because the volume was halved. Okay, so again, let's take a look. The concentration of your acid increases by 2, but the volume of your acid is halved. So the number of moles of your acid, which is given by concentration times volume, would remain the same. So for both experiments, the amount of acid and the amount of magnesium used is the same, which means that the volume of gas produced should be the same as well. So the correct answer would be A.